Hello, my name is Dr. Alexy Karenowska. I did an undergraduate degree here in Oxford in engineering science, then a doctorate in experimental physics. I now run a research group in the Department of Physics that works on magnetic and electromagnetic effects, and I also give tutorials to physics and engineering science undergraduates here at Magdalen College. It's a pleasure to be with you today, and I'm sorry that we're not able to meet in person, but I hope still to be able to give you a taste of what life here at Magdalen and Oxford more generally is all about. Now, my research and teaching interests are quite diverse, but when I was sitting down thinking about how to share them with you in the short time that we have, I realised that there's one theme that runs through all of them. They're all inspired by or focus on the value of things beyond those which we can see. So that's why my talk today is entitled Adventures with Invisibles. The history of my field, the science of magnetism, is a long one. Records from antiquity show us that scientists have been pondering the question of what magnetism is and where it comes from for more than 2,500 years. There are, of course, many areas of modern science that can trace their roots to antiquity. But magnetism, I would argue, occupies a special place because of the sheer length of time between the earliest recorded wonderings about what magnetism was all about and the development of modern understanding of where it comes from. The earliest record we have of someone pondering, for example, whether there was a connection between electricity and magnetism comes from the philosopher Thales in 500 BC. But it wasn't until the work of the great 19th century physicist James Clerk Maxwell that we really found the answer. And the reason for this is that magnetism is a unique phenomenon, an effect that's powerfully apparent. Naturally occurring magnetic rocks made from iron oxide can be found lying on the ground in many parts of the world and will attract and repel each other with great gusto. And yet it's so mysterious. You can't see it, you can't taste it. Our everyday experience of it leads us to believe that it only has an effect on an oddly narrow range of materials. And to really lift the lid on the physics that makes it happen, you have to have a very sophisticated understanding of the makeup of matter at the very smallest scales. When we stick a magnet to our fridge, we're effectively playing with one of the most subtle and beautiful symptoms of the quantum mechanical underpinnings of the physical world we inhabit. There is simply nothing else like it. So I run a low-temperature magnetic physics laboratory in Oxford. There's a picture of it here. In it, we cool pieces of magnetic material to a few thousandths of a degree above absolute zero and probe the properties of excitations known as spin waves. Now, a spin wave is a kind of magnetic wave. It's rather like a water wave, but rather than being defined by a moving variation in height of water, it's defined by a moving variation in strength of magnetic field. Now, spin waves have some very interesting properties. They occupy the gigahertz frequency range, so the same range of frequencies at which your mobile telephone operates, but they have speeds and therefore wavelengths which are much smaller than electromagnetic waves at the same frequency, which means that we can potentially build miniature devices or systems that have dimensions in the micron or even nanometer range that exploit wave phenomena to create new and interesting forms of information processing. Now, I'm particularly interested in how this might be done in the quantum regime. So what we do is build systems in which we can manipulate spin waves at the level of individual quantum packets of energy. Now, the quantum of a spin wave is called a magnon, and it's to be able to access magnons individually that we do our experiments at these exceedingly low temperatures. And going back to the theme of our talk, we can see that the kit we use to do our experiments is the opposite of invisible. It's a fascinating mixture of mechanical, electrical, and thermodynamic engineering. It's this that makes the investigations possible. But the work itself probes a physical effect, the spin wave, as mysterious and invisible as it is compelling. It only reveals itself to the most sensitive of instruments in the most specific of conditions. Now, in parallel with this research, I also work on the application of the same kind of science, magnetism and electromagnetism, to the preservation, restoration, and appreciation of cultural heritage. Now, much of the work that I do in this area has to do with using different parts of the electromagnetic spectrum, so everything from radio waves to X-rays, to image different kinds of cultural objects, everything from ancient monuments to textiles to manuscripts to ancient metalwork. And one particular area of interest is the preservation of cultural heritage in the Middle East, especially in Syria. Now, sadly, you'll probably be familiar with the campaign of cultural destruction that has accompanied the civil war in Syria. The Syrian people face a humanitarian catastrophe of cataclysmic proportions. Not only have people lost their homes, their livelihoods, their loved ones, but they also find their cultural identity under threat. This is the archaeologist Professor Khaled al-Assad, who was killed in the ancient Syrian city of Palmyra in 2015. The site was occupied by the group calling themselves Islamic State, and he gave his life to protect its most valuable treasures, objects that had been moved from the site for safekeeping. Around the time of his murder, they also demolished many of the architectural monuments of Palmyra, structures that had stood for nearly 2,000 years. And working with friends and colleagues in Syria, we use cutting-edge optical techniques to create a precise digital model of one of the most culturally important of these damaged structures, the so-called Triumphal Arch of Palmyra. It's a Romano-Persian archway that was built in the 3rd century AD. We then employ digital machining techniques using robots adapted from car assembly lines to cut the object out of solid marble and produce a 1/3 scale digital facsimile. The structure is nearly 20 feet tall and weighs 13 tons. We unveiled it to the public on Trafalgar Square in London of April 2016, and since then it's travelled thousands of miles around the world, raising awareness of the need to support the Syrian people and encouraging people to recognise the universality of the value of cultural heritage, whether it's tangible, that's in the form of objects or structures, or intangible, ideas, traditions, practices, and customs. It stood, for example, on the National Mall in Washington, D.C., in the Piazza della Signoria in Florence for the Cultural G7 in 2017, in the town of Verona, Italy, as part of a summer-long memorial event with the family of the archaeologist Khaled al-Assad, and in front of the United Nations building in Geneva, in connection with a major international conference about the protection of cultural property in times of conflict. And the interesting thing about this project is that it looks, at first glance, like an exercise which is all about something physical. Moving 13 tons of marble around the world is, after all, a very physical exercise. But it's not about that at all. Cultural heritage is really about people's connectivity to it. The difference between a monument and a pile of stones has nothing to do with the physics of stones. It has to do with the relationship that people, human beings, form with the monument, and in so doing, define it as one. We don't cherish the physical remnants of our past or the past of our loved ones because we consider the atoms and molecules of those objects we might have saved to be important, but rather because they are symbols to which we can pin our memories and they're repositories for feelings of attachment and fondness. Our arch is a visible object that stands not for its own sake, but rather in the service of something very precious and completely invisible, the hearts and minds of the people whom, for different reasons, the original object had meaning. And what I would say to you is that something a little bit similar can be said about Oxford. Oxford is an historic city. The university has been here for nearly 1,000 years, and the place is a maze of beautiful buildings, some imposing, some quaint, others practically monumental. But it's really important to realise that this physical structure is not the university. The university is the community of people, of hearts and minds that move around inside of it, all of whom are connected by a passion for learning and a desire to deploy it together in useful and meaningful ways. And extending our theme just one step further, all of our most important attributes as individuals also exist in a space beyond the physical. You can't see qualities like ambition, passion, or determination, and as brilliant as modern biomedical science is, there's no test for them either. But if you have these sorts of qualities, this university is a place where you will find a community of people from all over the world and from all different backgrounds, excited to welcome you and eager to help you to succeed.